Okay, great. Thank you very much for the opportunity to tell you all about work that I've been involved in over the course of the last academic year or so. This is work done in collaboration with R.V. Loeb, and it's work that is hopefully going to come out on the archive at some point soon. So the thrust of this work is to try and think about quantifying fine-tuning in such a way that we can apply it to various examples. And the kinds of examples we have in mind are sort of simplified examples where one can make sense of parameter spaces and observable spaces in a sense that I'll make more precise in a moment. This will allow us to think about examples in the context of astrophysics. And one particular example that I want to talk about is this idea, this proposal that primordial black holes can constitute much of the dark matter that we, in fact, detect. So what I thought I might do to start with is to just sort of lay down the conceptual landscape, talk about some of the philosophical issues that arise before launching into some of the more technical details. So as many of you know, fine-tuning can be expressed in the following way. That, and it's in blue here, that if circumstances were a little different, we would not exist. This is one particular statement of a manifestation of fine-tuning that people find particularly striking. Right? And this is kind of encoded in our current best physical theories, say, for example, the standard model of particle physics and the standard model of cosmology. There are a variety of concepts, even within this particular sentence, that I think are tricky to make precise. Some of them are more tricky than others. Some of the stuff in that sentence which is more straightforward is the notion of precisely which circumstances can change. So that refers to the kinds of theories that we have at our disposal, and we know how to make sense of those things. So those theories include equations of evolution for dynamical variables that we think are useful. They involve initial conditions for those variables which we specify, which we then go through, which then allow us to go through and solve those equations, and then also unspecified parameters that appear in those equations. So these are parameters which are not so the values aren't specified by the theory. We need to go out and measure them, and after having measured them, we can tell precisely what the theory predicts. So this is sort of something that's well understood to some degree. What is tricky and where the trouble starts is where you start to worry about what we mean by the notion of a little bit different. So this is where I think the heart of the issue of fine-tuning resides. It's a technical challenge. I think it's tricky, and it's the one that I'm going to focus on here. And then there's another interesting sort of conceptual issue that I think arises, namely this part of the sentence which corresponds to the claim that we would not exist. And you can pass this in the following way. You can ask, the non-existence of precisely what is supposed to be disturbing? There are all sorts of things that are finely tuned, right? So Tim Maudlin, a philosopher of physics, makes this point when discussing fine-tuning that I, for example, am a very specific, finely tuned quantity. But this should not mean that having noticed this, then we should go over to our fundamental theories and change parameters in such a way as to make me generic. Even I would not argue that that's a sensible thing to do, right? So the question is, what is the sort of most general thing that we should level our concern at? So is it the notion of life? Is it complexity? Precisely what? And once we've leveled our concern at that thing, then everything that's sort of more specific than that general concept can be thought of as arising via an accident, right? So I am an accident in this sort of conceptualization of the problem. Okay, so then the other question that arises is precisely how do we deal with finely tuned theories? So somewhat irrespective of how we define the notion of fine-tuning is this particular question. And one thing that you notice when you sort of either get involved in the practice of science, or if you read the history of physics, for example, is the fact that finely tuned theories tend to be a spur to theory development. Namely, we notice that theories are finely tuned, and then we go ahead and try and replace them with theories which are less finely tuned. So finely tuned theories seem to cry out for an explanation. There are a variety of interesting examples in physics of new, less finely tuned theories coming along and supplanting older, more finely tuned theories. And one example, an interesting example from the last 30, 40 years, is this example of cosmic inflation supplanting the standard Big Bang model of cosmology, which was dubbed as standard by Weinberg in the 70s, and inflation came along in the sort of early 80s and supplanted it. Of course, the question then arises, somewhat irrespective of how you make sense of the level of fine-tuning in the context of the standard Big Bang model of cosmology, whether inflation is itself finely tuned. And if you're interested in this kind of debate, there's a nice back and forth that occurred in the scientific literature about 5 or 6 years ago and has flared up again in the more popular scientific press, which you can read about, I think, in Scientific American in the last year or so. Okay, and then one other point that I want to make is that this idea of thinking about a lack of fine-tuning as being a virtue in terms of theory development, this is something that people in the vanguard of the emerging disciplines in science have in fact noticed. So it's probably not surprising. People who are working on things like theoretical biophysics or theoretical neuroscience know this. And so Bill Bialik, who is a sort of distinguished voice in theoretical biophysics, says the following, and this should resonate with many of you. He says, how can we reconcile the parameter aversion of theoretical physicists with the explosion of parameters that arise in a realistic approach to biological systems? Much of what our community is doing, I think, can be understood as a reaction to this problem. So our community refers to the people who are worrying about life from a quantitative point of view. And in a footnote, he says, one possibility, surely, is that the multitude of parameters is a fact of life, so to speak, and somehow irreducible, in which case we need to give up on our search for physicists' understanding. I'll discard this as too pessimistic. Okay. So this was the sort of the conceptual underpinning of the kind of calculations that we wanted to get involved with. And so what we wanted to do was then to develop quantitative measures of thinking about fine-tuning in sort of simpler circumstances where you can make sense of fine-tuning, in particular having in mind certain applications to astrophysics, with the view to try and aid the task of theory development, with the view to explicitly be able to compare different theories, to compare the level of fine-tuning that various theories are subject to. Okay. So what I'll do is I'll sort of discuss a local measure of fine-tuning that we describe, together with a global measure of fine-tuning, and then I'll use it to characterize fine-tuning in models where a significant fraction of the dark matter of the universe is thought to be in the form of primordial black holes. I don't think I'll have time to get to the second example, but we've applied it to other circumstances to characterize the degree of fine-tuning in these kinds of examples as well, in particular in astrophysical models in which the fraction of protons that end up in habitable dark matter halos is something that people have suggested. And we connect these kinds of models to cosmic inflation as well. Okay. So here is the sort of local measure of fine-tuning that we have in mind. It's essentially a local sensitivity, and you can think of it in the following way. That there are a set of parameters that any theory comes with, together with, for example, initial conditions, which you can lump into that set as well. And there's a transformation on those parameters to some space of observables. And this particular mapping can be extremely complicated, right? You can go from parameters via some dynamical system to some dynamical variables, and then you can think of an algebraic kind of operation on those dynamical variables which take those variables into some sort of observable. So you might think of this particular transformation as taking, say, in the context of inflation, parameters from the inflaton via the dynamical system, which is defined effectively by Einstein's equations, to various sort of dynamical state variables like the dark energy density, for example, and then also Q, the amplitude of scalar perturbations. And then these were mapped into something like the number of Milky Way galaxies, as an example. So it's going to be very complicated, and everything's sort of summarized in this compact form. You can then define the local sensitivity of the muth observable, assuming there's some large vector of observables, at some point p primed, which is supposed to correspond to something like your observed point, in some direction in parameter space. And we simply define the sort of muth component of this local sensitivity to be this. So this is essentially a dimensionless fractional change in the observable. And we take this limit, means we take the sort of order epsilon term. We end up with an expression which looks like this. And if you sort of unpack this, what this really is, it's sort of a derivative of O over O, divided by the derivative, so d on dp over p. And so it's the derivative of the logarithm of the observable divided by the derivative of the logarithm, with respect to the derivative of the logarithm of the parameter space, of the parameter. So in the case when O is particularly simple, it looks like this. Okay. So you have sort of m of these components, and you can combine them in some way. We combine them in a simple way using a simple Euclidean metric, and then you get one sort of general measure of local fine-tuning. And then for a single observable, which is what I'll be interested in here, this particular general measure of local fine-tuning takes this form. And you can think of L as the exponent in the power law dependence of observables on parameters. So d log O over d log P is L. That's the point that I wanted to make. And then this allows us to distinguish different orders of local fine-tuning based on the value of L. So for example, when L is exactly 0, there's no local fine-tuning, right? The observable is completely insensitive to the value of the parameters. And then when L is 1, so every value of L between 0 and 1, we bin into one particular category, and we call this local fine-tuning of order 1, and so on. But it's the case that local measures are not enough. It's not the full story, right? If the direction and parameter your space you're interested in points along a contour of the observable, then the local level of fine-tuning will be 0, but that's not going to be sufficient to convince you that, in fact, this observable is finely tuned. What you also need, and what we tend to point to, are global measures of fine-tuning. And so I want to just quickly introduce that too. So our global measure then computes how far one needs to travel in some direction parameter space for a significant change in the observable to occur relative to how far you could possibly have traveled in that direction. So what you do is that you're sitting at some point in parameter space, you're looking in some direction, you find the length of the vector such that you end up getting an order unity change in the observable. So it's an equation you solve for the size of V. And then you can compare the size of the range of the allowed parameter values in that direction to the actual value of the vector that you solve this equation for, and this gives you some measure of how globally fine-tuned the situation is. And I contend you need both of these kinds of measures to make sense of fine-tuning in the examples that I'll be talking about. So one other thing you can do is, instead of just looking in one direction, you can look in both directions. So you can look in, say, plus V and minus V at the same time, and you can ask how far do I need to travel in both directions to get this order unity change compared to how far I could have traveled in principle. And then the fraction, the ratio of that taken to an appropriate logarithm is then another global measure of fine-tuning, which I call G tilde. And then you can distinguish different orders, again, in the same way, by lumping various values of G into bins in such a way that you contend that these are, in fact, distinct in some sense. So, for example, when G is 0, you have no global fine-tuning. That's saying that the distance you need to travel such that you get an order unity change is, in fact, the entire distance you could possibly have traveled. So the observable simply does not change in that direction. And when G is 1, then the distance you could have traveled is 10 times the distance that you can travel to get an order unity change in the observable. Okay. So this is the sort of formal framework, and what I want to do now is apply this to a particular example. So the first example I have in mind is that of this proposal that all of the dark matter that we detect is in the form of primordial black holes, or at least a significant fraction of the dark matter that we detect is in the form of primordial black holes. And as many of you know, the primordial black holes were first posited about 50 or so years ago. They're hypothetical entities which are thought to arise from overdensities in the very early universe. They can be sourced by, for example, cosmic inflation, leading to these overdensities collapsing in the radiation domination phase of the universe. And there's been a resurgence of interest in their existence because of the discovery of these relatively massive black holes. So the order 30 solar mass black holes are tricky to create via the usual stellar collapse mechanisms. And so this is a separate way to produce such black holes. So one contention was that these black holes that were detected by LIGO and Virgo were, in fact, possibly primordial black holes. And then the fact that primordial black holes could constitute dark matter is an idea that's been around for about 40 years, and it represents a separate way of thinking about dark matter, distinct from particle-based ways of thinking about dark matter. Okay. So to describe fine-tuning according to these local and global measures that I've mentioned, we need to characterize primordial black holes in some way. And in particular, what we'll do, for the sake of simplicity, is invoke a general functional form for the differential mass fraction of primordial black holes. And it's going to take this, this particular form. It's a log normal distribution, and it's thought to be a decent approximation for certain mechanisms for their production. So certain inflationary mechanisms, for example, will give you this kind of distribution for the mass fraction. So this quantity here, F PBH, is the fraction, the total fraction of dark matter that's in the form of primordial black holes. And by fraction, we're talking about a density fraction here. So you end up with a 2-parameter log normal extended mass function. And there are a variety of constraints on the total fraction of dark matter that's in the form of primordial black holes, which this kind of mass function is subject to. And so you need to take that into consideration. You can't simply set F to be whatever it is that you want, of course. So here are some illustrative monochromatic constraints. So a lot of the constraints, as I understand it, come from the assumption that, that the mass function of primordial black holes is monochromatic, so essentially all the mass is one mass, roughly speaking. And these constraints come from various sources, namely considerations of primordial black hole evaporation, gravitational microlensing experiments. So this is the sort of evaporation constraints. These are the microlensing constraints, and then there are constraints from dynamical effects, which are a little bit here. And then there's constraints from primordial black hole accretion and radiation, which arise around here. And I've taken some example constraints from this particular paper to illustrate how this process would work. There are various updates on these constraints, I should say, but I'll continue with these for illustrative purposes. Okay, so there's been a procedure that's developed that allows you to derive constraints on the extended mass function, assuming that the observational constraints were derived under these monochromatic constraints that I just showed you. And the constraint that you need to satisfy is shown here. So this is telling you that the integral, the ratio of the extended mass function over the maximum value of the fraction of dark matter that's in the form of primordial black holes, assuming a monochromatic mass function. So that blue, the dark blue line from the previous slide, that ratio has to be less than or equal to 1. So if you go ahead and assume then a particular functional form for the extended mass function, and you take the upper limit here, you saturate the constraint, you can compute a fraction, so a maximal fraction of primordial black holes that are in the form of dark matter. And this maximal fraction is, again, just a function of two variables. So when you do this this integral down here, numerically, you end up with this plot. And what you're looking at here is, so this is the mass, and this is the width of the extended mass function. And you're seeing the maximal fraction of primordial black holes, maximal fraction of primordial black holes that could be dark matter. So, so what you'll notice is that there's a region here, for example, where this maximal fraction is in fact quite high. So this white region here corresponds to roughly 80%. So FPBH is roughly 80% here, and then it trails off as you increase the width because your extended mass function is subject to the constraints which it's running into at the edges. So if you zoom in on this little region here and you look at it really carefully, you see something like this. So here is a dot that I've selected which chooses a fraction, a maximal fraction of 80%, just to sort of probe the particular proposal that contends that a lot of the dark matter is in fact primordial black holes. And then you can compute the local fine-tuning level, right? So this is this expression that I showed you earlier. The parameters are given by the two natural parameters that arise in the problem. The observable is this maximal fraction, and epsilon is now just given by theta. So you can rotate around this direction and look at the value of the local level of fine-tuning, and you find this kind of curve where I'm just plotting the term that resides within these absolute value signs. And what you find is that you get a maximal local fine-tuning order of roughly 25. So whether that's big or not is a question. We can come back to that if you're interested. So then this notion of global fine-tuning, let me just show you this version in the interest of time. What you need to do, so this is sort of zooming out just slightly, and this is where the order unity change happens in the observable. the observable being this maximal value of the fraction. And so what you find is that you essentially get, in all directions, you get a decently globally fine-tuned scenario. So this is the case where I'm looking at global fine-tuning as extracted from an entire line as opposed to just a single direction. Okay, so one thing that you need to do, let me just point out, is that you in fact need to set a specific range of the parameters, right? So you need to assume that you can bound these in some sensible way. And I've chosen some values here for the sake of illustration, but this is sort of a component of, this is a necessary component of this analysis. Okay, and so let me just end on this point that this fine-tuning that I've in fact pointed out is expected to increase substantially if you trace the evolution of these primordial black holes from their actual origins. So if you have some model of inflation, which you then trace through all the way through to the extended mass function and ask about the level of fine-tuning, that I would expect that that would in fact increase. And it's an exercise that one could do, and it's an exercise which sits within the purview of this kind of approach. Okay, so I think I'll stop there. Thank you.
Eric? So it's a very, very elegant framework. I like it, but I have a slight worry about its generality.
Yes.
In the expression for the measure, there are all these parallel lines. I take it those are norms.
Yes.
But unless what you're doing is a scalar, which you are in your example, it's not clear to me that that for a lot of observables of interest, there's any physically significant norm. Like for a Riemann tensor, for conformal structure, the metric itself, I don't know of any physically significant norms on these objects, on families of these objects. So, but your measure is going to very sensitively depend on what norm you pick. So have you all thought about this, or?
Yeah, I mean, I think the sort of sensible, I agree. I think the general problem is difficult. I think problems which reach that kind of level of generality are tricky, and they're the things that I've sort of set aside on purpose, precisely for the reason that you mentioned. What I have in mind is thinking about fine-tuning in the context of these parameter spaces, which are sort of more straightforward to make sense of. So these sort of astrophysical scenarios are ones which are sort of ripe for this kind of analysis, and it would be tricky to deal with that kind of scenario here. So there's an assumption here that, for example, where I'm right, you're saying I'm setting down absolute value signs. This is certainly the case. I'm sort of measuring these spaces in a very naive kind of way. I'm just looking at the Euclidean norm, and you can say that you've assumed something like a uniform distribution, for example, over the parameter regions, and what's your motivation for that? Right, this is the conceptual issue, but apply this in the circumstance where it applies, is the message. Yeah.
Ramesh?
So Feraz,
Yeah.
you were looking at this logarithmic derivative as some measure of fine-tuning.
Yes.
I'm confused in my mind how you treat a parameter that is zero. So let's say I've got a simple theory, and then I've got a space of more complicated theories where I can introduce some extra parameter and give it a range of values. But my theory is zero, and let us say the universe is zero. Is that fine-tuned or not in your way of looking at it?
I mean, it depends on so it depends on what you could do with this parameter.
Yeah, let's say it can go from 0 to 1 or whatever.
Right.
Right? So let us call this a scalar field on top of GR or whatever, Right. Any theory you like, I can add an extra knob to it and look at a broader range of theories.
Yes.
And then I find that my universe actually doesn't have that extra knob. This parameter is 0. So at this point, I'm confused. In your language, should I then view my universe or my, theory as fine-tuned, or do we just say Occam's razor? This is actually a good theory, which is the way most physicists would approach it. But in your language, I want to know, is it fine-tuned or not?
You're asking whether in the theory without the extra dial.
Yeah, right.
Yeah. So, right, there is a phenomenological operational sense in which I'm performing these calculations, and that is that you've identified the relevant parameters. You've somehow, this sort of Occam's razor idea that you mentioned is the kind of idea that I have in mind, that you've in fact reduce the set of parameters that you're interested in to the ones that can vary in some reasonable way, and then you think about fine-tuning in that context. Right. But that doesn't, does that? Okay.
In the interest of the coffee break, maybe we can fine-tune the coffee break a little bit. So I'd encourage anybody that would want questions to go up to Feraz at the coffee break. Let's meet back here in 15 minutes and thank Feraz again.